Hello, everyone. Welcome to my presentation on coupling capacitance-based hidden state transition synthesis for sequential logic blocking. My name is Pratik Shrestha. I'm a PhD student at Drexel University, and my advisor is Dr. Yanis Savides. Here is an outline to this presentation. We start with an overview of hardware security. Next, we discuss hidden state transitions. Next, we discuss coupling capacitance-based hidden state transition, followed up with the security analysis of the technique. Finally, we make concluding remarks. Let's start with an overview of hardware security. Multiple untrusted parties are introduced to the IC manufacturing process as it moves to more global and fabless models. This introduces security threats such as IP theft, counterfeiting, overproduction, and Trojan insertion into different phases of IC design flow. Thus, security measures should be put in place to protect an IP from these attacks. Logic locking or obfuscation techniques are used to protect the IP from the aforementioned threats. An example of a MUX-based logic locking is shown here. The original IP is modified by adding special primary inputs called key inputs and key control logic gates such that the output is corrupted if an incorrect key is applied. The correct secret key is stored in a secure tamper-proof memory. Special logic locking techniques, such as Harpoon, have been designed for sequential circuits. In Harpoon, an additional FSM called obfuscated mode FSM is added to the original FSM called normal mode or functional mode FSM. An example can be seen in the figure. Here, in order to activate the locked IC, the FSM should transition from the obfuscated mode state S0 to normal mode state S5 through key input sequence P0, P1, and P2. These kinds of obfuscations, where FSMs are partitioned into obfuscated and functional mode and modified as required, such that the IP is activated using a correct key input sequence, are called entrance-type FSM obfuscations. Hidden state transition-based obfuscation also fall on the same category. These kinds of techniques are vulnerable to combinational SAT attacks if scan chains are accessible, unroll and SAT-based attacks if scan chains are locked, and FSM-based structural attacks as well. In this paper, we propose a coupling capacitance-based hidden state transition for sequential logic obfuscation. The proposed technique introduces critical modification to the IC at layout level rather than logic level, so the changes aren't seen if the IP is reverse engineered into a gate level netlist. A synthesis flow is developed to implement the hidden state transition to a circuit, and a security evaluation is also done using a random walk-based analysis. In the next section, we discuss hidden state transitions. Hidden state transition-based locking technique, as shown in the figure, has the critical transition between obfuscated and functional mode, masked or hidden. The hidden or masked state transition is triggered by applying an intentional glitch. This glitch forces the signal to miss arrival time window and the data to persist through the next cycle. Here we can see an example. In this setup, with 3 resistors having a maximum of 8 states, the second resistor is selected for the glitch. Normally, the transition from state 2 at input x equals 0 leads to state 1. But when the glitch is activated, the data in the glitched resistor persists, so the transition ends up in state 3 instead. This setup is leveraged to create a hidden state transition synthesis flow. Here, first an original FSM is partitioned into 2 by adding an additional state resistor. Then a SAT solver-based logic modification is done to accommodate the hidden state transition. With this synthesis, a k-bit key sequence is generated, which starts from the starting state of the obfuscated mode to the starting state of the hidden state transition. Then the glitch is triggered to transition to obfuscated mode. Traditionally, as the final step of synthesis, the glitch triggering mechanism is added by gating the flip-flop with a key such that the glitch is activated with said key. This trigger is visible in a reverse engineered gate level netlist. The diagram and truth table on the bottom right shows an example of a hidden state trigger based on gated clocks. In the next section, we discuss coupling capacitance-based hidden state transition. Here, the glitch is implemented using coupling capacitance and is not visible in the reverse engineered gate level netlist. In coupling capacitance-based hidden state transition, instead of gating the flip-flop, its clock input is coupled with a keyed aggressor line. When the aggressor is activated by the key, an intentional delay is produced by the capacitance, which causes a timing violation that triggers the hidden state transition. The initial steps for a synthesis of coupling capacitance-based hidden state transition is similar to the general hidden state transition flow. The FSM is partitioned and modified using a SAT solver to accommodate for hidden state transition. They, however, differ in the triggering mechanism implementation. The triggering mechanism consists of 3 steps. 1, adding an aggressor logic. 2, coupling the aggressor line with flipped resistor. And 3, adding variable delay to its data path. Our added aggressor logic should be logic high at the starting state of the hidden state transition and logic low on all of the time. It is then XORed with an inverted clock signal to create the final aggressor line. This line, when activated, is always the inverse of the clock signal, which maximizes capacitance delay at the transitions. Next, aggressor line is coupled with flipped resistors. In our experiments, a closed form coupling capacitance model is used to estimate coupling and ground capacitance based on interconnect length, height, width, and spacing. The estimated capacitance are then used in a pi model to simulate the effect of the coupling capacitance. Finally, delay elements are added to make any necessary adjustment. To test the proposed synthesis flow, ISCAS89 benchmark circuits are synthesized with TSMC 65 nanometer technology using Synopsys DC compiler. For the coupled aggressor line and clock line, for all circuits, interconnect spacing are set to be 25 nanometer and interconnect length is set to be 100 micrometer. Here are some results for the smallest S27 benchmark circuit. The timing waveform shows the final glitch clock line clock prime and flip-flop outputs HS for added hidden state resistor, N1, N2, and N3. N1 is the glitched resistor. When the aggressor is inactive, N1 changes from 1 to 0, but stays at 1 when it is active, effectively causing a hidden state transition. The graph on the right focuses on the clock transition in the 2 scenarios. The difference in the required time between the 2 cases are about 41 picoseconds. Here are average area and power overheads across all ISCAS89 benchmarks. Coupling capacitance-based hidden state transitions has an area overhead of 14.35% and power overhead of 22.02% compared to original unobfuscated circuit. This overhead is slightly higher compared to key gating-based obfuscation by 4.57% for area and 0.12% for power. Smaller benchmark circuits tend to contribute more towards the overhead, but in practice, IPs tend to be on the larger side. So considering just the 4 largest ISCAS89 circuits, coupling capacitance-based hidden state transitions has an area overhead of 2.23% and a power overhead of 1.25%, significantly smaller than the overall overhead. Next, we discuss the security of the obfuscation technique. Let's consider a threat model where the adversary's goal is to obtain correct input key sequence from a logged IC. The adversary has access to a reverse engineered gate level netlist and an activated functional IC also referred to as an oracle. In such case, the three possible sequential attacks are oracle-guided or SAT attack, FSM-based structural attack, or random walk-based activation sequence extraction. In SAT attack, the oracle is used to identify distinguishing input pair or DIPs. These are pairs which have different input outputs for the same key. A single pair can eliminate multiple possible candidate keys, so a SAT solver based on DIP quickly prunes incorrect keys away. SAT attacks are a critical threat to logic locking. However, an activated oracle only operates in normal mode, and hidden state transitions aren't even captured in the SAT clause for the solver formulation. Thus, the proposed method is secure against SAT attacks. In FSM-based structural attacks, the FSM is partially reconstructed and partitioned into strongly connected components or SCCs. These SCCs are subgraphs where every vertex is reachable from every other vertex. The source SCC and sink SCC can be used to distinguish obfuscated and functional mode. However, since the transition between the mode really doesn't exist in the gate level netlist, the FSM cannot be reconstructed, rendering this attack useless as well. For random walk-based security analysis, given a circuit FSM, we do a random walk through the state transition or S cycle in an attempt to reach the ending state of the obfuscated mode. A random walk score alpha is evaluated as the total number of traversed paths for all possible traversals, and the total expected number of paths is calculated. As an adversary, there are three possible scenarios for random walk attack. For case 1, the adversary is unaware of the implementation of hidden state transition. In this case, random walk never leads to a functional mode. For case 2, adversary is aware of the hidden state transition, but does not know which flip-flop is glitched. In case 3, the adversary is aware of the glitched flip-flop. The basic difference between case 2 and case 3 is that the synthesis is masked more effectively in case 2, which can be achieved by coupling capacitance-based hidden state transition. Here are random walk score and average expected number of paths for random walk for ISCAS2022 benchmarks. For different percentages of flip-flops triggered, we can see that as the percentage of flip-flops to analyze increases, so does the security measure. Here, setup with 100% flip-flop analyzed is analogous to case 2, whereas setup with 1 flip-flop analyzed is analogous to case 3. Compared to case 3, case 2 has 11 times greater random walk score on average, and the geometric mean of average number of expected path is 4,186 times higher. This shows that case 2 is more secure than case 3, and efficient masking of the glitching topology using coupling capacitance makes random walk-based activation sequence extraction harder for the adversary. So as conclusion, a coupling capacitance-based hidden state transition and synthesis flow is proposed to sequentially obfuscate a digital circuit. A power and area analysis is performed, showing an area and power overhead of 14.35% and 22.02% respectively, 2.23% and 1.25% when considering only the 4 largest circuits. And a random walk-based security analysis is done to increase random walk score by 11 times and geometric mean of expected number of paths by 4,186 times. Thank you.